Good morning, everyone. My name is Sudhir Malik. I'm a professor in the physics department. It's my great pleasure and honor to introduce you the speaker of today, Professor Hitoshi Murayama. Professor Murayama, he did his PhD from University of Tokyo in 1991 and has been a professor at University of California, Berkeley since 1995. He's also the director of Institute of Physics and Mathematics of the Universe. And he's known, he's a celebrity in our field. For me, it's like my two role models are sitting there. And he had been presented Yukawa Commemoration Prize, and last year he presented a talk at the United Nations, which was about using science as a tool for peace and development. And he's also a fellow of American Physical Society and American Society for Arts and Science. I hope I'm messing with some words here, but it's a pleasure to have him. So, Hitoshi.
Thank you for the kind introductions, and I'm amazed to see so many people, especially many of you have the final exam coming up, I heard. Good luck on that. And my first slide in Spanish, but I apologize, I don't speak the language, so I have to speak in English. But I just wanted to tell you first that if you are coming to this talk thinking that physicists or scientists in general is supposed to look like this, you're wrong, right? And I have 3 kids, all for your age. There are 2 of them in college, another one in grad school. And we are all sort of similar people working on interesting problems. And as Malik introduced me, I used to work in Berkeley for 20 more years. I still am there. But I started also start a new institute in Japan, just like Maida is doing here on physics and cosmology. So I became the director of the Kavli Institute for the Physics and Mathematics of the Universe. And then my friends in Berkeley start to make fun of me that, okay, this is way too long a title. Let's shorten this, keep the beginning and end of it, and make it to that one. That sounded like a lot of responsibility to me. And yet worse, it doesn't come with high enough authority, because back home, there's somebody who claims she's the voice of God. So I can't compete with that. Anyway, so what I'd like to tell you today is about this quantum universe, which is meant to be an oxymoron. We're talking about the universe as the biggest thing you can see. But I'm also talking about something quantum, that is about something as small as atom or atomic nuclei. What do they have to do anything to each other? And that's the connection that really fascinates me, and that's what I'm going to talk about today. So thinking about the universe, what we physicists do is to ask really simple questions like any little kid might do, looking up the night sky and start wondering, okay, this is so beautiful, get awed by the beauty of the universe, and then you start to think about, how did this universe begin? What is its fate? Where it's going? What it's made of? What are its base laws? And why do we exist in it? Where do we come from? And that's the kind of question I'm sure many of you ask yourself when you're little, maybe you still do. And that's the kind of questions we physicists also ask ourselves. For example, take this question, where do we come from? And this question has been in the realm of religion for many millennia, or in philosophy. And probably at the end of the 19th century or so, we started asking this question in the context of evolutionary biology. I'm not really sure if we are evolving in the right way these days. But anyway, this became a scientific question. And if you really want to understand where do we come from, the kind of machine you would love to have is this one, right? Time machine. And we do have kind of time machines for research. There are basically 2 kinds of machines we use for this. One of them are the giant telescopes. And if you have a big telescope, you can look really, really far away. And if you look billions of light years away, you're looking back into the past, billions of years ago. So this is the way you can really look back into the past, how the universe was like back then. So this is one type of machine we use. Another type of machine is called particle accelerator. That probably doesn't sound too familiar to you, but this is the way you can sort of redo the Big Bang, how the universe began. And so we use these tools to study how the universe was like and where we come from. So just to give you an idea of what I mean by this, well, this is the beautiful picture of Andromeda Galaxy. That's just our neighbor, but our neighbor galaxy is 2.3 million light years away. So if there's somebody out there pointing telescope at the planet Earth, what they're going to see is not like you, but like that. Because they will see how the planet was like 2.3 million years ago. That's the way you look back into the past. This is much farther away. This is called cluster of galaxies. About 100 galaxies are living together in a little village. And this particular one is 2 billion light years away. So if there's somebody out there pointing a telescope at us, looking at the planet Earth, what they're going to see is actually single-cell organisms. This is the farthest ever galaxy we've ever seen. So, if you zoom up this picture, you still don't see anything here, but here you see a red smudge. And that red smudge is a galaxy which may also have hundreds of billions of stars in it. And if there's somebody out there watching us, what they're going to see, well, nothing, because our solar system wasn't born then. So this is how you can study the past using big telescopes. And the best we have done, we now think the universe is 13.8 billion years old. So if you build a telescope that can look 13.8 billion light years away from us, then you're supposed to see the beginning of the universe. This is the picture of the Big Bang. You can see Big Bang happening in front of your eyes, literally. And that's how we know the universe began very hot and dense. Because we can really see it. But I actually cheated a little bit. This is not exactly the Big Bang. It's actually the surface of the Big Bang. What I mean by this is just think about looking at the sun, our sun. Can you see what's inside the sun? No. All you can see is the surface of the sun, right? Because the sun is such a dense, hot ball of gas. The light doesn't go through it. We can't see through it. We can't see what's inside the sun. All we can see is the surface. Universe is the same way. If you really would like to see what was going on at the very beginning of the universe, all we can see is the surface, because the universe as a whole was a hot, dense gas of tiny particles. And that's the way the universe was back then. So I can't see through it. So I can't really see the very beginning, but I see the surface of the Big Bang, and that is this picture. So it is some kind of wall. We can't see beyond that, unfortunately, with any telescope we can ever build. But of course, that would make us sad. Is there any other way of doing that? So this is the way the universe evolved, we think. Start with this tiny universe with a Big Bang, then start to expand all the way through. And this is where you're sitting in this auditorium thinking about where do we come from 13.8 billion years later. And using the telescope I have just shown you the picture of, you can see back to this stage when the universe was only 380,000 years old. Well, that sounds like a long time for us, but for the universe that's 13.8 billion years old, this is a really baby universe. It's amazing that we can really see the way the universe was when it was a little baby. So that's what we managed to do. But of course, to really understand where we come from, we also would like to know what was going on even before then. And then comes this tool, the other tool I mentioned, called particle accelerator. And this is something we have already managed to do. We can recreate the Big Bang in the laboratory to mimic the condition how universe was like when it was only 3 minutes old. It's a really baby universe. What you do is that, when the universe was 3 minutes old, you have this thick soup of tiny particles like protons and neutrons. And in the laboratory, we can throw them against each other. And then you discover sometimes they will stick with each other. That means out of proton or hydrogen, you manage to build helium, which you use for the balloons in birthday parties, right? So those helium actually in the balloons came from the Big Bang. So by doing these experiments in laboratory, you can tell that the Big Bang must have made helium with about 3-to-1 ratio to hydrogen. if you point telescopes to the sky and see how much helium there is in the universe today, it really turns out to be 3 to 1. So it works. We can really create the condition band and study how it was like in the laboratory, and then that will really tell us how the universe should be like today, and that actually works. So this is how we can study the universe when it was really, really, really young, when it was only 3 minutes old. So now comes this question, where do we come from? Well, this is a picture of my daughter on a very bad mood day. And we know she's made of atoms. And atoms have the nuclei at the center. And the nuclei are made of protons and neutrons. And we now know these things are also made of something called quarks inside. But never mind, I don't get into the details. So the question is this. I just told you the Big Bang made hydrogen and helium. But what are you made of? You need carbon, oxygen, calcium, iron. You need all of these elements to build up your body. Well, where do they come from? They don't come from the Big Bang. Then where else? That is actually a very interesting question we actually managed to solve. It goes back to this age-old question, why does the sun shine to give us so much heat and light? And actually, curiously, we didn't understand this question until the 1930s or so. It's actually fairly new in the history of science. And that's all thanks to this guy, you know him, Mr. Einstein. And he came up with this famous equation, E equals mc squared. And that actually turned out to be the key. So what's going on inside the sun is this. Just like what I mentioned, what happened in the Big Bang, you throw 4 hydrogen atoms against each other, and once in a while, they will stick to form helium with some byproducts. This one is actually antimatter, and another one here is called neutrinos, and I'll mention a few words about it in a moment. But the key here is this. So if you put this on scale, what you start out with is heavier than what you end up with. And that's odd, right? So if you think of collision of 2 cars, it's a violent accident, and a lot of debris fall over the road. But when the police comes, collects all the debris from the road and measure them up, that should be exactly the same amount of mass as 2 cars you start out with, right? And that's what we learn in school. It's called conservation law of mass. Mass is never lost. But here, mass is lost. What do you start out with? And what do you end up with? What do you end up with lighter than what you started out with? That is the key, because the amount of mass you lost, and its mass, can turn into energy. So this is what the sun is doing. So the sun is shedding its own mass and turn that into energy. So as we speak, our sun is getting lighter by 4 million tons every second. It's literally shedding its mass and turns that into energy to give us this abundant heat and light. You know, I really wish I could do this. I can take this mass into energy. That would be wonderful. Anyway, I don't know how to do that. But the real question then is that, okay, that sounds like a very plausible idea, but how do we know this is true? I have told you already, we can only see the surface of the sun, not what's going on inside. But this must be happening at the very core of the sun. So how do we know? Well, there is actually a way of doing that. So I mentioned these neutrinos. They are very shy, tiny, small particles. And they are so shy that they don't interact very much. They can just get out of the sun without any trouble. So if we can manage to see these neutrinos, then you can look back into the center of the sun directly. And as we speak, there's so many neutrinos coming towards us from the sun, about 100 trillion neutrinos are going through your body every second. This is a huge wind of neutrinos coming from the sun. And you might think I'm crazy, we're inside a building, right? But as I said, the neutrinos can get through the sun without any problems. This amount of concrete is nothing to them. Entire planet Earth is nothing to them. You are always exposed to this wind of neutrinos coming from the sun. Does any of you feel this wind of neutrinos coming from the sun? Oh, there's one man. I seriously recommend you see a doctor today, okay? So how do we actually see them if they're so shy? Well, the simple idea, let's build a big target. Well, they are so shy that maybe once in a while, they might leave some trace of it. They might produce a little kick inside in an experiment. And this is one of those. This is called a super cameo candy experiment. And what you see these round things is sort of electric eyes to see light. Each one of them is like this. What you also see is two graduate students, poor students on a mission on a rubber shaft. This is the big water tank. And inside the water, the neutrinos might leave a little trace so that you can see a flash of light. But because they are so shy, most of the time, the only thing you see is noise coming from some contamination inside water. So you need to make this tank incredibly clean. It's very big, like 120 feet high, 120 feet wide, but you need to make this humongous water tank incredibly clean. So that's where these graduate students come in. They on this rubber shaft, take a piece of cloth, put alcohol on it, and just light this electric eye. 1, 2, 3, all the way 420 feet. And then they fill water a notch to get the next level. Start wiping, 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 all the way along. And the whole process would take about 3 months because this water tank is so big. Well, just in case you're worried, they do get bathroom breaks, dinner time, they go home during the evening, so anyway. But using this big target, you can actually manage to see these neutrinos coming from the sun. So that's why we know what's going on at the center of the sun, because you can see it with this water tank. So these ghosts are meant to be neutrinos. You don't see them normally, but once they come into this water tank, once in a while, they leave a little bit of trace seen by these electric eyes. It still doesn't happen very often. There are so many of them coming here. It's such a big tank of water, but still they manage to see only like 10 a day. But just imagine you're trying to take a picture of some faraway star. You need to keep the exposure of the camera open for a while that you get enough light to take a picture of it, right? The same idea. In this case, you take the exposure open for 5 years, then you can take the picture of the sun, even though this water tank is 3,000 feet underground, in pitch darkness, no light comes in, but you can see the sun. This is the picture of the sun taken with neutrinos. Not just the picture of the sun, this is the picture of the center of the sun. That's how we know the sun is a factory to build bigger and bigger atoms. That's what the sun is doing. And not just our sun, also some distant stars. This is a picture of a star that exploded at the end of its life in a nearby small galaxy called Large Magellanic Cloud, which is about 160,000 light years away from us. And that explosion also produced so many neutrinos that some of them had been detected by a smaller tank that existed back then in 1987. Small in this case means 1,000 tons, but that's the small in this community. And as I've been told you already, most of the time, the only thing you see is noise, because the neutrinos are so shy, you're looking for these teeny tiny signals of neutrinos. So all you see here is noise. But for just a split second, they came neutrinos in a big burst. Da, 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 da. Well, it's only 11 of them, but nonetheless it's a burst. Something explosive must have happened. And when astronomers turned their telescopes to the sky, lo and behold, they did find an exploding star called supernova. So you can even see the inside of these faraway stars without ever going there. And this is an incredible discovery that earned Nobel Prize to a physicist called Koshiba. And you know, this noise, of course, is a problem. And it turned out that they'd been fighting with this noise all along, and it was only a month before this discovery that they managed to keep the noise down. And this is actually a very rare event. The supernova explosion may happen only like twice a century, and you certainly don't want to miss it. Another amazing thing is that a month after this discovery, the Mr. Koshiba was subject to a mandatory retirement. There was only a 2-month window, and exactly at the middle of 2-month window, and 160,000 years before then, the star had exploded. And that's how I managed to see these neutrons coming from a supernova. So, students among you need to remember, to succeed in science, sometimes you need to be amazingly lucky. But this way we have learned that these distant stars far away, 160,000 light years away from us, are also made of atoms. And it's also a factory of building bigger and bigger atoms. So that's something we have learned. It's a very important thing. So putting that together, Big Bang made hydrogen and helium. First generation of stars were made only of hydrogen and helium, but they started to build bigger atoms like carbon, oxygen, and iron. But even if they are made inside, if you cannot take them out, where do you come from? You can't build your body if they stay inside the star. But very luckily, as I told you already, these stars may explode. After building these heavy atoms, they just disperse them into space, and they became dust in empty space. And that dust gets collected again to form the second generation of stars. They are children. And they keep making more bigger atoms at their cores, and then they explode again and spits out this dust into space. You collect them again, then come the third generation stars. From what we know, our sun seems to be the third generation granddaughter of the original star. That's why when sun was born, he had already plenty of these heavier chemical elements, calcium for your bones, iron for your blood, oxygen for water. Those things were already there. And when the sun was made, a little bit of debris eventually became a piece of rock, which we call planet Earth, and it had all the ingredients you needed for your body. So that's what happened. So my daughter came from the supernova that also produced a Nobel Prize. So one take-home message here is that you are stardust. You came from stars. Okay? And thinking about the end of the life of stars, of course, our sun would eventually come to its end in about 4.5 billion years from now. It would run out of fuel. It can't produce energy anymore. It can't sustain its own weight. So the center of the sun just collapses, and everything bounces back, and the sun becomes very big. It doesn't quite explode. Sun is sort of medium-sized star. It's not heavy enough to cause a humongous explosion like supernova, but it bounces back and becomes very big to the extent that it's going to swallow up our planet. That's the end of the planet Earth. So, you guys are young, so you still have time to think about how to get out of this planet in time, okay? You gotta keep working on that. And it seems like there are actually plenty of places we can actually move to. We used to think that the planets exist only in our solar system. Solar system, we thought, was a special place. But it turned out, these days, there have been many planets found outside the solar system. We call them exoplanets. This picture is a satellite called Kepler, launched by NASA looking for these exoplanets. We already have some 2,000 candidates of planets outside the solar system. And some of them seem to be sort of Earth's size. And of course, the right planet has to be not too close to the star, then all the water becomes steam and you can't build your body. If it's too far away, all the water then becomes ice. You can't live with ice. So you need to be at the right distance. But if you can find so many Earth-sized planets in other systems, you're bound to find some of them at the right distance, with atmosphere, with a rock you can stand on, and so on. So there is probably some places we can move to. People even manage to take a picture of some of these planets outside the solar system. And actually, this is a legacy of Puerto Rico. There is a big radio telescope called Arecibo Observatory on this island that discovers some of the first examples of planets outside the solar system. So anyway, maybe we can find a new home later on. Now coming back to this question where we come from, I have told you where the center of atoms, nuclei, came from. They came from stars. But we need one more thing. We need to have these tiny particles with electrons happily move around inside atoms so that your body can be made. This actually had not been understood until 3 years ago. It required the discovery of a new particle called Higgs boson that is filling up the entire space and thus keeping the electrons happy to just go about inside the atoms. And I'd like to tell you this story too. So that happened again with this one of these particle accelerators. This is the world's biggest accelerator of all. It's like 17 miles across in circumference. And this is in the Swiss-French border region. And just to appreciate the size of this tunnel, which is underground, this is the airport of Geneva. It's bigger than the runway at the airport. And this entire 70-mile circumference of the tunnel, underground tunnel, is filled with high-tech device. And this is circle, but it's so big that even if you get inside, you have to pay a careful attention to tell that it's actually is not straight. It is that big. And these objects are real high-tech devices called superconducting magnets that are meant to keep these tiny particles already inside this ring all the way through, and it can keep accelerating. So that's what these particle accelerators do. So it's like, sort of like a hammer throw. You just keep circling things around, and then gets faster and faster. At the end of the day, you smash them against each other, and that mimics what was like in the Big Bang. Well, you can't really do the Big Bang, but maybe you can do a little bang, and that's exactly what these machines are meant to do. And using this machine, they have discovered this new particle. And this was really exciting. You know, this happened on July 4th, 2012, that's 3 years ago. And this had been long in the making. The first idea that our universe is filled with this new particle called the Higgs boson, a very strange idea that came about 50 years ago. And people started to take this seriously and start to think about how to do an experiment to test that idea about 30 years ago. Then people start to build this experiment about 15 years ago. It's been long in the making. So this was an announcement made at the CERN laboratory in Europe. It was webcast around the world, was viewed by millions of people actually. I was one of them, watching it at my home, Berkeley, midnight. And after this announcement, I literally wept. It was so moving. We finally understood why we exist. And especially because this happened on July 4th. I went to bed afterwards and woke up, and we all got together and celebrated the Higgs Dependence Day. And this was humongous excitement around the world. It was covered by media all over, and it was that exciting day. And you know, two people who were introduced today, Maida and Sudhir, they actually built this detector. If you smash these particles against each other and cause this little bang, so many things fly out from this, and you would like to make sure you can capture all of them. That is also a pretty big machine to do that. And this machine is called CMS. C stands for compact, but you can see this is the size of a person compared to this. So this is meant to be compact. So Maida and Sudhir, Professor Malik, actually made this huge instrument so that we wouldn't miss anything that comes out from this little band. So many things come out, you would like to capture them all. And I really admire them because they can build these humongous instruments. Thousands of people from around the world come together. They bring in their own piece and make sure that they would fit with each other and work with each other. People coming from different countries, like people from Russia and Ukraine work together. People from Israel and Palestinians work together. Indians and Pakistanis work together. It's really a peaceful collaboration in the world. And there's also a competing group called Atlas, which is actually even bigger than CMS. That's why this is meant to be compact. And both groups have been very serious about trying to tell people why they're doing this, what are they after, how they're doing it. And so this is one of such outreach videos the Atlas group has made. So let me show that to you. Oops. I hope there's sound. So this is how the protons come together. It's a little bag that produces so many particles. Now you can see what all the different particles they have this studio. And they are pretty serious. Now keep watching. Really good, huh? So it talks about how this international group of people made this happen together. And this is how the Higgs boson was made. So this is a CMS detector. Protons come from both sides. And then you see this flash of particles coming out from this. And you see these yellow streaks. And they are particles of light called photon. And so when you make this Higgs boson, sort of sadly, it actually disintegrates right away. And what you can see is fragments of the Higgs boson. In this case, Higgs boson fragments into two particles of light, photons, and that's what they can see with this incredible device. So we discovered it. But what exactly did we learn from this? Well, what we learned is this. When the universe was hot, do you know what it means to be hot? For example, the steam coming out of a volcano is very hot. And something hot means tiny particles in there, in this case water molecules, are zooming about at an incredible speed. So if you feel very hot on one day in the summertime, the air particles, molecules are zooming about so quickly, they will be hitting your face all the time, and that's what you feel to be hot. So hot means everything is chaotic and random. But once you actually cool things down, like in the case of water, eventually it becomes ice. And ice is water molecules lined up so neatly. So cooling things down means you go from chaos or disorder into an order. And that's exactly what Higgs boson did. Higgs boson used to fly apart. It's complete chaos and random. But as the universe cooled, then eventually the Higgs boson froze into empty space. It's everywhere. It's right here, everywhere. It's frozen into empty space. When did that happen? It happened when the universe became cold enough for the Higgs boson to freeze in, and that was as cold as 4 quadrillion degrees. At that temperature, Higgs boson filled up the entire space. It's frozen in everywhere. And that's exactly how we can exist today. Because the electrons that are happily moving about inside these tiny atoms, they actually want to go at speed of light. They would like to zoom away. But because it keeps bumping on this Higgs boson that's frozen into space, they get slowed down, and that's how they are happily going about. So if for some reason, the Higgs boson that's frozen in here evaporates right now, then your body would disappear in a nanosecond. It is the Higgs boson that keeps you together. It's a very important thing for us. So after this discovery, I was invited to a primetime news show in Japan, and the newscaster there asked me a very simple question. Okay, Mr. Murayama, you've been telling me that this Higgs boson thing is everywhere. But if that's true, why didn't we notice that before? Good question. I had to think for a while, and eventually answered the question in the following way. It's just like the air. If it's there all the time, you take it for granted, you wouldn't even notice. How do you know there's air right here? You can't see it, you can't touch it, you can't smell it, you can't taste it. How do you know? I think the reason I know is that my parents told me that. But if that wasn't the case, how would I have actually figured this out? The only time you might know that something actually exists is that there is some motion to it. That's the wind. You can feel the wind. But some ancient folks thought there is something called wind. They didn't know that was the motion of the air. So if everything is around you, is always there, you take it for granted, it's very hard to figure that out. The Higgs boson is like that too. It's always there. You were born into it, it's hard to tell. But if you can make motion in that, maybe you can tell. But no matter how hard you try, it's so rigidly frozen into space, you can't really make it move. You can't push it that hard. The only thing you can do is to take a big hammer, whack on empty space, and the Higgs boson that was already there, one of them might pop up, quickly disintegrates, but you can see its fragments. And that's exactly what this experiment has done. Large Hadron Collider, LHC, is a huge particle accelerator. It's a big hammer. With that hammer, you struck empty space, the vacuum, but Higgs was already there, so it popped up. And that's what you observed. So that's exactly how it happened. The next question she asked me is, oh, okay, that sort of makes sense, but how do we tell the story to the general viewers? What is the best way to do that? Again, I had to think a bit. And I asked her to bring in a bunch of kids to the studio. Let them just run around like crazy. That's how the early universe was like. But then comes this magician called Higgs boson. There was an actress who came to take the role of the Higgs boson, and then she cast spell on the kids. And all these kids running all like crazy magically calm down and eventually sit at their own desks. These desks are the nuclei that came from stars, and the kids are the electrons that slowed down by the Higgs boson, and there we go. That's the atom. That's what you're made of. But the real question then is, who is this Higgs boson? What does he look like? From what I can tell, it is a strange, faceless guy. And it's a very strange thing. And it seems to be one of its kind. So does he have actually any siblings or relatives? We still don't know a whole lot about this particle called Higgs boson. What I mean by this is this. Every tiny particles we have seen before are spinning like a top. It's an eternal top. It's spinning forever. Every particle, electrons, photons, quarks, dimensions, every one of them is spinning forever. If something is spinning like this, depending on how you look at it, they look different to you, right? So in some sense, they got face. But this new particle called Higgs boson doesn't spin at all. It's faceless. It looks completely bland, smooth, nowhere to latch on. It's one of its kind. We have never seen a particle like this before. That's why I'm calling this a faceless particle. And it sounds so strange to me. When I first thought of this idea, when I was back in grad school, I had to learn this idea called Higgs boson, and I couldn't believe it. You know, it's the most important particle in the universe, right? Some people even call this God particle. But if you bring in an idea of particle nobody has seen before, and let it do the most important job in the universe, that doesn't sound right. Sounds very easy or artificial, so I couldn't believe it. So after I got my PhD degree, I collaborated with a couple of people and proposed Higgsless theories. But now that it's discovered, So recently, when I go to international meetings, pretending I'm a proper Japanese, I've been apologizing like this. Sorry, I was wrong. But it still leaves this very uncomfortable feeling about this. This faceless particle, is that the only one out there? Or maybe it has siblings and relatives? Maybe, it sounds crazy, but our space, we think is 3 dimensions, up and down, front and back, left and right, the 3 ways you can move. But maybe our universe is actually secretly 4-dimensional, 5-dimensional. There may be extra dimensions that are curled up in such a small size we haven't managed to see them. A Higgs boson may be actually secretly spinning, just like any other particles. But if it's spinning in these extra dimensions, you don't think it is. Maybe that's what's going on. Or maybe it's not an elementary particle at all. Maybe it's made up of some smaller things. And after all these questions, we still haven't understood the very important question: why is this only this particle that flows into the empty space of the universe? We don't understand any one of those. So there's still some research we have to do, and by the studio, they're working very hard on these questions using this particle accelerator. And this idea of extra dimensions might sound really crazy to you, But if this idea is really true, extra dimensions are also supposed to be everywhere. Curled up in small size, you don't see it. So it's sort of like this. Now, if you're actually on this cable of Golden Gate Bridge in San Francisco, it's close to my home, and this guy there can only move forward or backward. So he thinks it's a one-dimensional space, sort of, right? But the little ants on this cable not only can move forward and backward, but it can also go around the cable. These little ants think they are on 2 dimensions because 2 directions it can move. So tiny things can see more dimensions of space than big things. And this is actually a seriously talked about theory called extra dimensions. Maybe we're going to find those extra dimensions also with this particle accelerator. We'll see. But anyway, Higgs boson is the reason why atoms exist. That's where you come from. It's there. But still, we haven't quite understood what exactly it is. So that's where we are. But then comes even more interesting question. I told you it came from stars, but where do the stars come from? Well, I told you that the atoms exist thanks to stars and Higgs boson, but how were the stars born? Where did they come from? Once you get to this stage of the question, actually we don't know the answer yet. It seems to do with something very mysterious called the dark matter of the universe, which is totally mysterious to us. We don't know what it is. But this seems to be actually the key to this question, where do the stars come from? We know these weird things exist because if you take a picture using telescope, sometimes you see a picture like this one. Can you see it from the back? Maybe, can you turn down the lights up on the stage? Is it possible? Well, hopefully you can see it. This kind of looks cute, doesn't it? You see 2 eyes, nose, mouth, frame of the face. And this, this is a real picture from the telescope. It looks so cute. You got a nickname. It's called Cheshire Cat in Alice in Wonderland. But the strange thing is this. These eyes and nose, they are round. They are the ordinary galaxies. Made of like 100 billion stars each. But what is this thing, mouth? It's really, really stretched out. What's the frame of the face? That's also really, really stretched out. Are there galaxies like that? No way. Because if you have a galaxy of this shape, then they want to fly apart very quickly. They can't stay together very long. You would not see them. So what is that? It turns out that this is actually a trick played by dark matter. Not only this one. This is the picture I've shown to you earlier today, and this is the cluster of galaxies. 100 galaxies are living together in a village, but you see also something really, really stretched out. Do you see that? Also here. This one is very long. Also out there, and also here, and this one too. Again, there can't be galaxies of that kind of shape. It looks really stretched out. And that's another trick dark matter is playing on us. So what's going on here is this. If you have a lot of dark matter here in this cluster of galaxies, and just imagine there's a faraway galaxy in the same direction behind that cluster of galaxies, then the light coming from this faraway galaxy actually gets pulled by the gravitational pull from dark matter, and they get bent. So the gravity of this dark matter acts like a lens. It's like a magnifying glass. And you might have this experience that if you look at the very edge of the magnifying glass, you don't see a very clear image. Things get so really, really distorted. It's exactly like this. So dark matter acts like a lens and playing tricks on us. So if you do a computer simulation, imagining that there are tons of galaxies behind that are flowing behind this the dark matter, then this is how they're going to look like. So when the galaxy gets behind this collection of dark matter, then it looks like it's really, really stretched out. But after they pass through behind it, then they will turn back into their normal shapes. Because nothing happened to them. It's just a trick played by dark matter by bending light. It looks stretched out to us, but nothing really happened to them. So this is actually great. We don't see dark matter directly using the telescopes, But if they are playing tricks on us, you know where the tricksters are. You can tell where they are. And this is wonderful. So if you take a picture of faraway galaxies, like this one, and forget these really bright crosses, they are actually nearby stars. What we like to study is these little dots. They are faraway galaxies, like billions of light years away from us. But with the modern technology, you can make out the size and shape of those galaxies, billions of light years from us. And then you can tell they have been stretched out. So dark matter is playing tricks on us, and that allows us to figure out where the tricksters are, and here they go. So this is how dark matter is there out in space and playing tricks on us. And one of my colleagues in Japan doing this study is right here. This young professor working with his young assistant. And with this kind of study, they figure out that more than 80% of matter in the universe is this mysterious dark matter. You probably learned in school that everything's made of atoms. That's wrong. 80% of matter in the universe is something unknown to us. It's mysterious. We call it dark matter because we don't see it, but we don't really know what it is. So it's actually very important to us. And this is another dramatic picture of what dark matter actually does. So this is a beautiful picture of clusters of galaxies, about 4 billion light years away from us. But this is actually really ugly place that it's good that we are not there. So what's painted in pink here is gas made of ordinary atoms, helium and hydrogen, that got heated up to such a high temperature, it's emitting, lighting up with X-ray. So that's in this pink. What's painted in blue is where dark matter is. We could figure it out by this trick played on us by them. So this is dark matter, this is gas. Here's another dark matter, is gas. So this is one cluster of galaxies, here's another cluster of galaxies. But something is wrong with this picture because the dark matter and gas are separate from each other. Dark matter and gas are also separated in the other cluster of galaxies. That can't be true because dark matter is supposed to provide this gravity, and gravity pulls things in, so they are supposed to be together, but they are separated. And people studied hard on this question, and eventually we understood it in the following way. This is an aftermath of a collision, high-speed collision of two clusters of galaxies at a speed of 4,500 kilometers per second, more than 3,000 miles per second. An incredible collision. And you can redo this in a computer simulation. So a cluster of galaxies is basically a ball of dark matter sprinkled with this ordinary atoms, just a tiny bit in them. And when they collide, atoms will interact with each other. They get heated up, there's a friction, they slow down. But the dark matter just keeps moving as if nothing has happened. And there we go. That's how we can understand this picture. So dark matter is definitely there, but it's also a very strange thing. It doesn't interact with itself, it doesn't interact with the ordinary stuff, so it is kind of spooky and scary. So here it is. But it's also very important because dark matter is actually our mom. So I've shown you this baby picture of the universe, right? And it was a very enhanced contrast, but when you actually look at it, it looks very, very smooth and bland and nothing interesting and boring. Everywhere looks the same. But if there's a tiny bit of more dark matter in one spot, and that gravity puts more stuff in there, and it becomes denser, gravity becomes stronger, put more stuff in, becomes more dense, stronger gravity, more dense, and eventually gets this kind of contrast over time. And where there's a lot of dark matter at the end of the day, puts ordinary atoms in there, and atoms will scatter against each other, they emit light, cool down, and coalesce into stars and galaxies, and that's how stars and galaxies were born. But in a computer simulation, which he does, you can simulate a universe which is wrong, that it doesn't have dark matter in it. Then if you do the simulation, 13.8 billion years later, nothing. It looks totally boring, bland, No stars, no galaxies, no us. So stars were made thanks to dark matter. That's what I mean, the dark matter is our mom. But we never met her. We got sort of separated at birth. We would love to see her and thank her, but we never managed to do that so far. Who is she? Well, again, we have to study this question. But anyway, so the story of how stars were made, this is actually done in this wonderful video clip, that this guy is George Smoot. He is one of the first person who took this picture of the baby universe, and he got a Nobel Prize for it. And after he got Nobel Prize, university asked him to do something interesting. And this is what he decided to do. He decided to reenact the Big Bang using marching band. So let me play that.
I really admired the band, and so when they said we wanted to react to the Big Bang with the guys from your lab, I said, no way, I want the band. Okay, so now I gotta tell you what the Big Bang is so you guys can do this before the sun goes down. Okay, so the idea is everything in the early universe was packed together very densely. It may have gone for infinite. We don't have infinite people, so we just have to use what we got. And everything stretched, right? Everything got bigger. And the further away you are, the faster you go. So we're going to want to start at the beginning with everybody packed dense and jostling around and playing high tempo rapid.
So there's a Big Bang.
Then at the mark, everybody moves apart.
Expanding like
people
crazy.
on the outside moving faster than the people on the inside. And there's a little bit of irregular motion, so miss some steps. Okay? I know you can do this. Right? And then what happens is you're going to coalesce together in groups of 6. Right? So you have to find 6 buddies. And half of you are going to form spiral galaxies. 3 people facing one way, 3 the other, and you rotate slowly as you move out. And the other half form elliptical galaxies, which are round blobs that keep moving out. So now, there's a brass section out there called tubas. They make a really spectacular spiral galaxies, a really big one, like our own galaxy or like Andromeda. So you guys get to be near the middle, and you get to make a really cool, you don't have to run out so fast, but you get to be able to orient where half is facing the other way, and you get to rotate with a sort of twist up. And you're like the centerpiece of this whole thing. Go tubas. Great guys.
And George told me that they actually didn't rehearse once. They got it on one shot, everything right. So that's pretty amazing. But what you do need to remember though, that 80% of people there are mysterious dark matter. And George himself is at the center of Milky Way galaxy, which means he is a supermassive black hole, which is 4 million times heavier than our sun. So you don't get to see most of these things in the universe. But anyway, this is how we were born. Thanks to dark matter, we collected ordinary gas together by their gravity, and they came out stars and galaxies and us. So it is really our mom. But we would like to know who she is. We have some idea who she might be, and we call that WIMP. It's sort of like monster neutrinos that can easily pass the entire planet. And the WIMP stands for weakly interacting massive particle. So they're heavy objects made in the Big Bang. They are still out there. So we think these tiny particles are actually the dark matter of the universe. Then you have an idea. We've been there before. We try to detect these almost invisible particles like neutrinos by going underground, because underground is very quiet. You don't have much disturbances there. And underground is like this. I used to walk underground myself. I brought my family one day, and it's really, really dark. But anyway, so you build instruments in there. In the United States, there is a similar underground experiment in South Dakota, and this is one such experiment. People are trying to look for dark matter. And you see physicists are happy people, dancing like this. And there's similar laboratory also in Canada. This one is really, really deep, about 2 kilometers deep, like 1.5 miles. And if you go that deep, you get closer to the center of the Earth, so it actually gets hot. The surface of the rock, 2 kilometers deep, is actually hot. You can't touch it. So it's that deep. And going to those deep locations, people run experiments trying to actually see a little clink made by dark matter by listening to them very, very carefully. But I told you, this huge tank has seen 10 neutrinos a day. These experiments, if they're lucky, might see 2 dark matter a year. You gotta be really, really patient to do that. And some people are not patient, like Maida and Sudi over there. They say, well, we can't wait that long. Okay, let's make it. If Big Bang made the dark matter, maybe we can do that too. And it's actually not easy to do because you don't see dark matter, right? But if you throw particles in this way, and it also come from the other way, smash in this head-on collision, and if something comes in a head-on collision, then there's no difference between up and below, left and right. Everything has to come out in balanced way. But if you see something like this, something's interesting. A lot of things going upward, but nothing downward. That can't happen. Everything is supposed to be balanced. Then you say, oh, I know what it is. There are invisible particles going that way to balance them out. So by measuring everything you can see and then subtract them, you can tell how much invisible things are made. So this is what they're hoping to see. Maybe we can make dark matter one day. You see, these particle accelerator experiments are really, really amazing. You bring in very light particle called proton. So they're like tricycles. And you speed them up. And then, wham! You crush them against each other, right? Then, what you hope to see is like, times the equal mc squared, planes and tanks come out of that. You want to convert your energy of the tricycle into the mass of these big objects. And some of these heavy ones might well be the dark matter of the universe, and that's our mom. So, by doing these things, how far can we get back to where we come from, namely the Big Bang? I told you about when the universe was only 3 minutes old. That's when the helium was made. Dark matter, if that idea is right, was born back here when the whole universe was only 1/10 of a billionth of second old. And if we understand it correctly, this Higgs boson thing froze into empty space when our universe was only like 1 trillionth of a second old. We are getting pretty close to the Big Bang. That's how we try to understand where we come from. But then, that of course makes you wonder, what about this? Can we really get there? Can we study it? Well, that's an idea called inflation here. Namely, universe started really, really tiny. How tiny? Entire 13.8 billion light years we see today was smaller than the size of an atom. Even smaller than the size of an atomic nucleus. It was microscopic, minuscule. And that minuscule universe got stretched out by this incredible expansion we call inflation. And can we tell if that really happened? Okay, so why do we think that to begin with? Well, these days we have done many of these astronomical observations, and to see where the galaxies are, what shape, what color, and what distance, if you put that information in a computer based on the real data, you can pretend in a computer to fly through space like this. If we really want to do this, you have to fly at a speed about 10 trillion times faster than the speed of light. Don't try this at home. But the message is, no matter how far you go, things don't seem to change very much. It just keeps going forever. Well, there are some parts that are kind of more denser in galaxies, some parts that look a little bit empty, but more or less, just things keep going forever. Every area looks pretty much the same. So that's how the universe is. Practically the same, no matter how far you go. And if you make this in a two-dimensional map, it looks like this. So this map is 2 billion light years across. You see some dense spots, some empty spots. You see these wrinkles. But again, more or less, things just keep going like the way they do. It doesn't seem to change very much. And this is actually a very strange thing, right? Because the light coming from that direction, billions of light years away, they have just reached us. They didn't have time to reach the other galaxies billions of light years were over there. But then, why do they look so similar to each other? Why does that part of the universe and the other part of the universe, they could never talk to each other, but why they look the same? Something is strange. How was it arranged? And the idea then is, well, maybe everybody was together at the beginning. In this tiny, tiny, minuscule universe, everybody was so close to each other, they've been talking to each other a lot, that's how they became the same. Then inflation stretched it out. That's why they look so much separated from each other now, but they were actually in communication back then. That's how they know to look the same now. But if they are like that, then what produces these wrinkles? A little dim spots, a little empty spots, and that was needed for dark matter to build up stars. Where did that come from? And this is a very strange idea. It comes from the uncertainty principle. When the universe was incredibly tiny, tiny world is governed by a theory called quantum mechanics. That's the quantum I was talking about at the beginning of my talk. And this quantum mechanics predicts that energy may not be conserved after all. You can borrow a little bit, as long as you can put it back in. You can lend it somebody, as long as you can get it back later. And the universe is doing that all the time, so it's always fluctuating like this. So empty space is actually active. This is empty space. Doesn't look empty at all. Everybody is borrowing energy, lending energy all the time. It's a very dynamic place. As long as you can put them all back in. But suppose you borrowed a little bit of energy, but the universe is getting stretched at incredible speed, then, hey, I forgot to give it back to you. And if you lend a little bit of energy to somebody else, you're not going to get it back anymore. So you're stuck with what you borrowed, what you lent, and that is how the universe became a little bumpy like this, only a little bumpy. Think of 100-meter deep ocean, and you're talking about only a millimeter ripple on top of it. Only a tiny, tiny variation of density and temperature, but that is what was made by this quantum uncertainty principles. And that became this contrast in temperature in a picture of the baby universe. And that became the origin of these wrinkles that eventually got amplified by dark matter to form stars and galaxies. And that's the idea. So if dark matter is our mom, inflation is our dad. You need both of them to be here. How do we know this is true? Well, this inflation was such an incredible expansion. Something of the size of a bacterium becomes as big as a galaxy the next moment. It's incredible expansion. And if the universe is getting stretched like that, the space itself starts to wobble. And that wobble becomes what we call the gravitational wave. It may influence this light coming from the Big Bang itself and leave some telltale pattern in it. And that's something you can actually look for. My colleagues at my institute in Japan are trying to launch a new satellite called the Lightbird, trying to look for this wobbling space produced by this inflation itself. So this is sort of reminiscent of another thing that Receiver Observatory has done. By looking for the radio signal, they managed to find these binary pulsars. That was the first evidence that space can wobble in what we call the gravitational waves. So in a similar way, if you can use this radio to observe the light coming from the Big Bang itself, you may be able to tell this pattern left by this wobbling space came from the inflation itself. That's how we might know that the universe really did start with this incredible expansion from tiny, tiny size, smaller than the size of an atom, that got eventually stretched to this 13.8 billion light years across big, big universe. And this research, of course, led to another Nobel Prize. So we'll see. So if we manage to actually do that, then we will be able to see back to this point when the universe was incredibly young, incredibly tiny, and that's how we try to make progress on answering the question, where do we come from? So what physicists do is actually very simple. We ask these very naive questions about the universe. Where do we come from? Where are we going? I mainly talked about this question, where do we come from? But as you also saw, all these questions are pretty mingled up with each other. They are all interrelated. And that's the kind of mysteries we hope to solve. So we would like to win this battle against the mysteries of the universe. Thanks for your attention. Thank you.
I guess we have some time for questions. Please come to the microphone so everybody can hear. Any question?
Yes, hello.
Hi.
My name is Edward, and excuse me, I'm not a physics student, I'm an art student, but I'm very interested in this theme. And maybe you already answered this question, I'm still going to ask it, and if you did so, please explain it with a little bit more specificity. I understand that, if I understood well, the Boson-Higgs actually slows down particles, although it's frozen. And I see that as a very similar effect that the WIMPs or the dark matter has. It actually contains things. So I would like you to talk about the relationship between, for example, the boson of Higgs, and how does it relate to gravitational fields and the manipulation of light in space-time, as it was proposed by Einstein. You know that light actually comes in gravitational fields bend space-time, so it becomes, perceptual time becomes slower or faster depending on where you're positioned by it. So I see that as a change in acceleration or speed, and I think the boson of Higgs does a similar thing, so I would like you to explain that.
Amazing physics questions from art student. I'm very impressed. and I really mean it. You know, they're actually excellent questions. So about gravitation and the Higgs boson, the first question. So Higgs boson is frozen so rigidly everywhere in the universe. It's very difficult to make any dent in them. You can't make it more dense somewhere and more sparse somewhere else. So they are totally uniform throughout the entire space. So even though they probably do feel gravity, it doesn't pull anything in one particular direction or one particular place because it's totally uniform. So the Higgs boson, it doesn't pull anything in a particular way, so it doesn't seem to show any impact on gravity as far as we can tell, because it's totally uniform. But dark matter, it concentrates. You have a lot more dark matter here, right here in this room, compared to totally empty part of the universe, about 1 million times more here. So dark matter becomes dense, gets accumulated, and that's how it draws ordinary matter in there to form stars and galaxies. Dark matter now has a big variation between dense spots and empty spots. So that's the main difference between their behavior. Are they related? Well, we don't know. If you ask the question if dark matter and the Higgs boson are related to each other, you're asking about something we just managed to discover, we don't quite know what it is, to something totally mysterious. Are they related? Well, we don't know. But a lot of people think they might be. For example, I mentioned this idea that the Higgs boson may be secretly spinning in extra dimensions. And particles that are moving in extra dimensions, they also exist. And if they're moving in extra dimensions, we think it's not moving because we don't see the motion, but it's moving actually, so you've got energy, and according to Einstein again, energy looks like mass to you. So particle moving in extra dimensions look like a heavy particle to us, and that might be the dark matter. So in that sense, they may be related, but again, we haven't answered that question yet. So we're still waiting for new data from these people so that we can understand it better, I hope. Does that answer your question? Good. Thank you. Yes?
Hi.
Oh, there's a whole line.
Yes. I have like a zillion questions, but I will try to explain to. If the Higgs particle is fixed in the space now, and it makes sense to us that we are somehow experiencing that, well, like the air that you mentioned, that we don't know it's there because we know it's there.
Right.
But the universe is expanding, so those Higgs particles are outside the universe that we're moving to, or they're moving with the universe? They're already there, or?
Yeah, that's also a very interesting question. So this is the way it seems to behave. As the universe becomes, say, twice as big, the volume becomes 8 times bigger, you would think that everything would thin out, but Higgs boson doesn't. It just keeps weighting up to maintain the same density. It has this really weird behavior.
So it's moving and not moving at the same time?
So it's not moving. The universe gets bigger, but Higgs boson is sort of left out there, and is still with the same rigid, compact.
So it's already there.
It's already there. Yeah, that's right.
So we have no idea how far it is.
Yeah. And of course, where is the universe expanding into? Again, nobody has seen that, so we don't know.
Okay. And the other question is that when you mention the correlation of the space far away in the universe, that it looks very alike.
Right.
And we know about the entanglement. Can they be moving or changing through time, but because they are entangled, they don't know what to do?
Yeah, that's an excellent question. For those of you who don't know, entanglement is actually a very specific technical term in physics, which happens in quantum mechanics, that what is out there and what is over there may secretly be in a very funny combination. The minute you tell it's pointing that way, you can also tell the other one is pointing the other way. So that's called entanglement. And this uncertainty principle, this active empty space I mentioned, is actually entangled. It is. But when you actually stretch them so far away from each other, then they tend to forget about this now. And it's called the classicalization. So what used to be entangled now becomes a real variation in energy intensity. And that's how inflation produced these wrinkles that eventually became stars and galaxies. So at least that's the idea. We need to prove it.
So before we get questions from here, we have a question remotely from Andrea Biedra. So can you hear us? Yes, so I passed my cell phone to Hitoshi.
Go ahead.
My name is Kenneth out there. I'm a high school physics teacher. And the notion that the Higgs boson doesn't spin in three-dimensional space is interesting to me. And I'm wondering what type of experimentation, the possibility that it might spin in other dimensions, what type of experimentation is taking place to identify those other dimensions?
Okay, thank you for the question. And there's one thing that our friends here are actually trying to do. So again, if you smash particles against each other, once in a while, something that flies out from this little band may go into those extra dimensions. If something is moving in extra dimensions, you don't think it's moving, but got energy, so you think it's very heavy, so E equals mc squared. So these experimentalists can look for these extra heavy particles which are actually moving in extra dimensions, and that's the way they want to prove that these extra dimensions do exist. So there is a way of doing real experiment to see if there really are these extra dimensions to space. I hope that answers the question. I guess we have to move on. So I guess this line says.
Yeah, sorry, my English is a little rusty. It's about entanglement.
Oh.
I got here quantum entanglement. It says an effect can create an effect in the universe, in other time and space in the universe. What is that thing that makes them entangled?
Yeah, that's another sort of spooky thing about quantum mechanics. Are you a physics student?
No, but I like this.
Oh, okay. So it sounds really strange, and I completely agree with you. And Einstein actually himself didn't believe such a thing can happen.
Spooky reaction.
Yeah, it's called spooky reaction at distance. But all the experiments show that that is really the case. And Einstein's objection, why that can't be true, was that if you do measurements over there, instantly you know what is supposed to happen over there. It looks like you are sending information faster than the speed of light. But people actually tried hard to think of a way of sending information using quantum entanglement, and the answer turned out to be no way. Because you have no way of knowing if the measurement here would turn out to be this way or that way. And of course, then you know what should happen over there, but you haven't transmitted information from here to there. So it turned out that Einstein was most likely wrong, and entanglement is possible. It's a spooky sort of connection between this part of the universe and that part of the universe, but you can't use it to transmit any information, so there's nothing wrong with it. So it sounds spooky, but at least we know there's nothing wrong with it.
Also, basically, they are saying that telepathy is possible, right?
What is possible?
Telepathy, like two particles. We are made of particles, so I can connect with another human in other space.
I don't know about that, but I guess it's logically possible. Yeah, I believe so.
So, last question. Physicist says the double hole experiment that the observation of the subject can create an effect on the photon particle. So they are basically saying that when we are not looking at the particle, it behaves like a wave, and when we are looking at a particle, it behaves like a photon.
Right.
So, what is that?
Yeah, so that's also a very good question, and people are still debating it. What exactly happens when you look at it? So there's this famous paradox called Schrödinger's cat. So if you keep a cat inside a box for a while, if you're not watching, you may be either dead or alive. You don't know.
So it's the influence, right?
Yeah. The minute you look, you find the cat dead, or maybe alive. But at least either way, the outcome becomes clear. Before looking, it's not clear. So that is what quantum mechanics does. And at least every experiment done so far is consistent with this idea that if you're not looking at it, it's sort of wave-like object. You don't know where it really is. But once you look at it, your position becomes fixed.
So it's basically saying you can create yourself the outcome.
But you can't. It's not that you are creating the outcome. So the fact that you looked at it, of course, leads to an outcome, but you can't predict what that outcome would be each time you look at it. And over time, if you keep doing the same measurement over and over again, you can start to see a pattern. But each time you can't predict. So you are not in control of that. Okay.
Since we have several people in the lines, I will request to be short in the questions because time is limited.
Ask one question.
Hi. Sorry, I have to call. My name is Luis Diaz. I'm a computer engineering student here at Mayaguez, and I have a question. I'm just gonna spitball something, because I see physics and the mysteries of the universe as software. It's like software that's running, and physics is just trying to hack it. We're just gonna try to see how it actually is. You can't see software while it's running. You have to stop it for a little while, then you have to analyze, and you have to analyze the output, which is what we see. So I'm just gonna spitball something. What about if Higgs is actually space? Like Higgs is space, and between Higgs is true emptiness, and between the Higgs moves everything. Higgs, space, as you said, it's frozen, so it's actually space. Well, in the 3 seconds, it wasn't frozen, it was actually moving. So after it was moving, when you said about the things about space as borrowing energy and then it got separated, what about if dark matter is still Higgs while it's still moving? So that's why we kind of see it. It's just a spitball. I'm trying to hit an atom with a hammer, with a hammer that's smaller than the actual atom. So I'm pretty sure I'm going to be wrong some way, but I'm pretty sure that you're going to say why, and it's going to be really interesting.
Well, so about Higgs being space itself, if it's just space and nothing else, even if you bring in a hammer and try and knock it out, it doesn't come out, right? Because it's just space. So it's clear that something is there.
Yeah.
That's actually in space, not space itself, but something in space.
Well, it's emptiness.
Yeah, but it's part of what we think is emptiness, because we take it for granted, it's always there, but it's actually not really empty, just like the air. So it's there.
It's there, and things are moving between them. So does the Higgs particle behave like a neutrino? Like, do we move between Higgs, or do we carry the Higgs with us?
It's sort of that we are dragging Higgs with us. That's why we acquire mass. That's why we don't go at the speed of light.
Okay, so it was just a spitball. Thank you.
All right.
Okay, hi, my name is Rosie. I'm a curious artist. And correct me if I'm wrong, but you said that before the 3 minutes that Earth was like basically being born, before that, where is science going with that study? Like what happened before the 3 minutes that you just said?
Before 3 minutes?
Yeah.
Well, so talking about this original dark matter stuff?
Yeah.
And the question
and
was
how
actually...
how Earth was created basically, like before the 3 minutes. Because like you started like explaining after the 3 minutes. So before that.
I guess what was before Big Bang?
Yeah.
Is that the question?
Yeah.
Before the Big Bang. And I would say it's still a complete matter of speculation right now. So I told you how far we are trying to look back in time, and we may be able to reach this inflation eventually. We're not there yet. And you asked me the question, what's even beyond that?
Yeah.
And so right now we have absolutely no clue. So some people think that universe started out with Big Bang, but then stops some moment, and then collapses, bounces back, that's another Big Bang, stops, and collapses, bounces back again, that's another Big Bang. So some people think that the universe is actually cyclic. In that case, answer to your question is that before the Big Bang, there was another Big Bang, before then was yet another Big Bang, and so on. That might be the answer. This is not a very popular theory, I have to say though, because if the universe keeps bang, 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 eventually becomes like a dirty rug. It will be pretty ugly, but our universe looks very smooth and clean. So this idea is not very popular because of that observational fact, but some people still think that's the case.
Okay, because I've always wondered, because like the Big Bang theory, like it's basically from the middle, like to where we're at here.
Mm-hmm.
And another question is like, what can you tell me about gravitational force? Is it just an influence?
Yeah, so gravity is also another very interesting question. And we used to think that gravity is a force that is pulling these massive objects towards each other. But Einstein changed that idea. According to Einstein, gravity is not a force. It's sort of an illusion. We are moving always straight, but space itself is curved. So if we're trying to move on, let's say, surface of trampoline, which is curved because of somebody's weight, you think you're moving straight, but because it's curved, you eventually find yourself coming back to where you started with. And that's how our Earth orbits around the sun. So gravity, according to Einstein, is not a force, it's an illusion, it's rather the impact of space and time itself, somehow curved. So that's the idea, and all these other things I mentioned about gravitational wave right now supports that idea. And even your GPS in a cell phone doesn't work if you don't believe in this idea. So it's actually quite established theory.
Okay, well, thank you.
All right.
So may I request be very brief in questions and just ask the question, don't like debate or go back and forth, because there are many people here. And we have 5 more minutes, and I think we need the speaker to have lunch so that he can feel more energetic now. So like few more questions, but just ask the question quickly.
Hi, my name is Pedro. I'm a physics student. My question would be, why do we need to assign a spin to a particle? Why can it have just no spin?
Well, that's a very good question too. So at least all the particles we have seen so far, except for this one Higgs boson, they all have spin. And we think there is a reason for that. And the idea is that if the particle is faceless, it doesn't have spin, then it's very difficult to keep that particle very light. And so people use this analogy that it's sort of trying to bring in a pencil and let it stand upside down. If it's perfectly balanced, it may stay that way, but you don't believe that, right? It will eventually fall down. So Higgs boson is that kind of unstable object. And if you don't have spin, it looks like that. But those things that do have spin have sort of are protected. They are much more stable. So there is this idea that spinless particles, faceless particles, should be dragged up to very, very high masses so that we will be beyond the reach of any experiments, but we have seen it. So what is keeping control of this? What is making it stable? And that's where the idea of extra dimensions and another idea called supersymmetry come in. If you're studying physics, you might eventually get to that. So we feel still very uncomfortable about this spinless particle being so light.
Thank you.
Okay.
Hello, I'm Ariel, and my question is, if I understood correctly, how is that the Higgs boson doesn't change or unfreeze with all the energy that is received from all the other particles that is colliding?
So the different particles would bump on Higgs boson with sort of different rate. An electron is a fairly light particle, so even though it does bump on it so that it doesn't fly above the speed of light, it doesn't do it very often. Other particles are heavier, so they bump on Higgs boson with sort of higher rate, and they get more mass that way, they get slowed down more. So different particles will interact with this Higgs boson in a different way. Why do they do that? That's something we haven't understood it either. So that's part of this mystery about the Higgs boson. Why does it interact with different particles with different rate? Excellent question.
Good morning. You know a lot about space, and I was wondering if you believe in aliens.
I do. And as I told you, there are so many planets out there. And even in our neighborhood, we already discovered 2,000 candidates. So I think it's quite likely that in some of them, the planet made of rock, with the right distance from the star, with liquid water, with all these other material needed to build up biological systems, there are probably aliens somewhere.
Thank you, and I believe the same.
Okay.
Good afternoon.
Oh, Star Wars.
I'm not a student of physics, but I'm a student of microbiology.
Huh?
And my question is, how come quantum entanglement and the Higgs boson may be able to explain the theory that there is, or they may exist, multiverses or multiple universes?
Yeah, that's an excellent question too. So people do talk about this multiverse idea a lot these days. And that is because if you look at the laws of physics we have understood so far, everything seems to be adjusted just right. If you just change some of the numbers, or what we call the natural constants, a tiny bit, you seem to get a very different kind of universe. And here's a simple example. So we know a nuclear made of protons and neutrons. Let's just make neutrons, they are pretty much the same mass within a 1 per mil actually. But let's make the neutron maybe 20% heavier than proton. Then all the neutrons would decay into proton in that case, and there will be no chemistry. There will be only hydrogen, no other atoms. If you do it the other way around, if proton is a little bit heavier than neutron, all the protons would decay into neutron, and there are no atoms at all, because nothing would have electric charge. So they need to have exactly the same kind of masses, so that all the entire periodic table exists, so that you would exist here too. So the idea of multiverse is that we probably can't explain why things are adjusted so well. It may be just random. And there are different kinds of universes with different kinds of natural constants, and most of them wouldn't lead to any intelligent life form like you, so that you wouldn't be asking that question in that universe. Only kind of universe that had the right conditions, right set of numbers and natural constants that will lead to intelligent life like yourself, then you will be asking this question in that kind of universe. So that's what people talk about the multiverse. So different universe may have different size of the Higgs boson, different mass for the dark matter, different size of the forces and so on. So people do talk about that. Maybe last question?
Hi, my name is Juan, and I wanted to ask you a question about, you were talking about how the universe was mostly uniform, that most of it was mostly the same no matter where you go. I had a question about the Eridanus constellation, where they discovered a super void of 1.8 billion light years across, where they say it's more empty than it should be, and for its size, it shouldn't really exist. Like, it's underdense. Could you tell me how that could be?
Yeah, I don't think there's anything wrong with that actually. So if you, again, do this kind of computer simulation, starting from very bland, boring universe with only tiny variation in it, then if you just push the button, let the computers do the rest of the work, just because of gravitational pull. Gravity only pulls, it never pushes. So it accumulates things in dense spots, and that would leave some of the empty spots out, because they all lost all the dark matter into those dense spots. So it does create these voids eventually. So it's just all done by gravity.
Oh, okay, well, thank you.
Okay.
Okay, well, I guess we should end the stream of questions here, and you are very welcome to email Professor Murayama, and he can reply or wait for his reply when he gets time. So before you disappear, I must thank all of you, and I must thank the Center for Hemispherical Cooperation and their staff, and my associate dean who made all this possible, and physics department Professor Rafael Ramos and his staff who made this possible, and also Professor Mayra Velasco. My personal thanks to make this event happen here in Mayaguez. And in the last, I would like to present a souvenir to Professor Murayama. This does not have dark matter inside, but it does. But you're curious to know what is inside it. Inside this, there is a mug of coffee, so that he can be awake and find solutions to some of the questions. And there is also water, a bottle, so that he doesn't feel thirsty. And then there is another hot mug, so that he can put some dark matter soup in it. And so, thank you so much.